Hi students, welcome back to Physics for All YouTube channel. In today's session, I am going to explain about diffraction grating. This diffraction can be grating is an optical component that disperses or split and diffracts the incident light into several beams or several colors, and these colors are traveling in different directions. The directions of these beams depend upon the spacing between the grating lines and also depending on the wavelength of the incident light, which makes diffraction grating very essential tool in the areas of spectroscopy, telecommunications and various scientific applications. Now we can discuss diffraction grating, how we will get the diffraction equation. Now it is arrangement of large number of parallel slits of the same width or same thickness. These number of slits are separated by equal opaque spaces. Now the ruled lines are opaque to the light, but the space between any two successive lines are transparent to the light. Therefore, whenever light is incident on the lines, then each and every line acts as a slit. Now let us consider E is the width of the each line and D is the distance width of the slit, and A plus D is known as grating element. Now let us consider capital N is the number of lines per inch on the grating. Then grating equation can be written as N into E plus D is equal to 1 inch. Already we know that in 1 inch is equal to 2.54 centimeter. Now finally we can write here E plus D is equal to 2.54 divided by capital N. This is in terms of centimeter. Now we will discuss about diffraction grating. Now whatever the pictures you are seeing on the slide, it is nothing but diffraction grating which is already using in the engineering physics laboratory. On this diffraction grating, 15,000 lines per inch are present. Now whenever this diffraction grating is kept in the diffraction grating stand, now allow this grating for a light ray, then this incident light get diffracted by the number of parallel slits arranged on the grating. Then this incident light get diffracted by the slits, then we will observe the diffraction pattern or spectrum on the screen. If you will observe the spectrum on the screen, it contains several orders. N is equal to 0 is called as principal maximum, and N is equal to 1 is the first order, second order, third order and so on. These orders can be seen on both sides of the diffraction pattern. Now already we derived equation for the grating equation. D sin theta is equal to N lambda, where D is the distance between the adjacent grooves or grating spacing, theta is the diffraction angle, N is the order of diffraction, lambda is the wavelength of the incident light. Now we will see dispersive power of the grating. Now dispersive power of grating is defined as the rate of change of diffraction angle with respect to the wavelength of the incident line. Mathematically, this equation can be written as diffraction of the nth order principal maximum is equal to A plus B sin theta is equal to N lambda into capital N. Let us say equation number 1. Now this equation number 1 can be differentiated. What will get? A plus B into, in the place of sin theta, d by d theta of sin theta becomes as cos theta. Again differentiate d theta, that is equal to N capital N into d lambda. Now as per the definition, we need rate of change of diffraction angle with respect to the angle. This can be written as dispersive power. So d theta by d lambda is equal to N into N divided by A plus B into cos theta. Equation number 2. Equation number 2 refers dispersive power of the grating. Now from this equation number 2, it can be concluded that dispersive power of the grating is directly proportional to the order of the spectrum and number of lines per centimeter, and it is inversely proportional to the cos theta. Now if this is a laboratory grating and we are observing diffraction pattern on the screen. Now coming to the resolving power of the grating, it is important for examination point of view. Now the resolving power of a grating, it refers the ability to distinguish between two closely spaced wavelengths of the incident light. It measures how well the grating can separate these wavelengths in the diffraction spectrum. That means if resolving power of the grating is more, that grating can disperse the colors more number of orders. If resolving power is low, that grating can disperse the number of orders into low number. So mathematically resolving power of the grating can be detected by using the equation. Resolving power is equal to lambda by d lambda, that is equal to lambda divided by d theta into d theta by d lambda. Now here how we got this equation number 3 on the right hand side. We are multiplying with the d theta and dividing with the d theta. Both are going to cancel. We will get the same equation. So therefore, in order to get resolving power of grating, we are multiplying d theta and dividing with the d theta. Now already we know from the previous slide, a plus b into sin theta is equal to n lambda. Now differentiate this equation on both sides. So a plus b into sin theta becomes as cos theta into d theta, n into d lambda. Now write this equation in the form of d theta by d lambda is equal to n divided by a plus b into cos theta. Now the diffracted rays from the grating enters the objective or the telescope in the grating spectrometer. If diffracted beam completely fills the objective and width of the beam equals, then it will disperse the colors into different orders. Now we have to calculate angular limit of the resolution of the telescope. D theta is equal to lambda divided by d. Now apply cos theta. Now d is equal to ab into cos theta, that is equal to L into cos theta. Here ab is the length of the grating and d is the distance between the grating and the source. So in the place of L, in the place of ab, we are writing L into cos theta. Now write equation for d theta, that is equal to lambda divided by L cos theta. This is how we got this equation. Substitute the value of d, that is L cos theta, in the above equation. D theta is equal to lambda by d. So d theta is equal to lambda divided by the place of d, substituting L into cos theta. Now modify this equation as lambda divided by d theta is equal to L cos theta. Now we need to derive equation for the resolving power, that is equal to lambda divided by d lambda, that is equal to lambda by d theta into d theta by d lambda. Now in the place of lambda by d theta, substitute L cos theta. So L cos theta into the place of d theta by d lambda, use previous expression, that is n divided by a plus b into cos theta. Now in this equation, a cos theta and cos theta both are going to cancel. The remaining equation write as n into L divided by a plus b. Now in this equation, in the place of L divided by a plus b, where is a plus b? Just you go through the equation carefully. In the place of L divided by a plus b, we are writing capital N. Therefore resolving power of the grating is equal to n into capital N, where n is the number of rulings on the grating and it is the nth order of the spectrum. This is about resolving power of the grating. Now this is a laboratory setup of resolving power of the grating. This instrument is called as grating. Now when laser light is incidenting on the grating, this incident light get diffracted on the screen. Now this is a first order, it is a second order on the left hand side. Similarly, it is the first order on the right hand side, it is the second order on the right hand side. If resolving power of the grating is more, then this grating can disperse as more number of orders. Now in this example, only we are seeing only two orders, first order and second order, because of low resolving power. This is about diffraction grating, dispersive power of the grating and also resolving power of the grating. If you have any doubt, please comment me in the comment section. Please like this channel and share to your friends for getting more number of updates. In the upcoming session, I am going to explain you about another new concept. Thank you.